All right, so let's try to get through this video. Now, I did this, and the more I think about it, I don't know that we really need this on the test, but it's just good for you to know that the reason hydrogen is here and not with the nonmetals is that hydrogen acts like these things here. The periodic table is arranged in order of how things behave. So I think we'll get back to this. I don't want to deal with this right now, so I'm not going to deal with it. But we call the groups by different things. So these are transition metals. These are alkali earth. These are you may know the noble gases are the last one. The halogens are the ones right before the noble gases. And we'll talk about that. But they're arranged by properties. Groups run up and down and periods run left to right. I think I do want you to know the words group and period. I think. I don't know. It comes back later. So you'll learn it by the end of the year. So either learn it now or learn it later. I don't think it's on the test, to tell you the truth. But anyway, groups run up and down and periods run left to right. There you go. All right. So elements, metals have luster. They're mostly solid. They're ductile, which means they can be sort of pulled into wire, and they're malleable, which means they can be hammered. They're good conductors of heat and electricity. That's very important that they're good conductors. The nonmetals, on the other hand, are more brittle solids, gases. They don't conduct. That's important that they don't conduct. And they come in a variety of colors and supposedly dull. I should get rid of that. I don't know why I have that up there still. That seems rather judgmental. All right. Metals are on one side of the staircase. And if you ever forget which side, just look at the names of some of the elements and you'll figure out which ones are metals. The non-metals are on the other side of the staircase of the periodic table. And then the metalloids touch the stairs. And the thing about metalloids are they're semi-everything. So they're semi-metallic and semiconductors. Because these are conductors and these are non-conductors. So they're going to kind of be in between on that spectrum of going from metals to non-metals. All right. I want you to know that ionic compounds are compounds that have a metal plus a non-metal. So if you have something from one side of the staircase and something from the other side of the staircase, that would make an ionic compound. Examples are salt and any kind of solid like that. Potassium carbonate, baking soda is an ionic compound. And we'll talk about what that means as the year goes on. But for now, it's never too early to get in your head that a metal plus a non-metal is ionic. So you will be expected to know that on the test. And then covalent compounds are when two nonmetals get together. And that makes like wax and water. And they're not going to be quite like the solids that ionic compounds are. They come in more varied shapes and sizes and gases and liquids and whatnot when you have covalent compounds. All right. And then we did do solid liquid gas. We did this on the FET. None of this should be news to you that solids have definite shape and definite volume, and liquids have definite volume but indefinite shape, right? They take the shape of their container to some extent. They don't go all the way to the top like gases, and gases definitely have neither volume nor shape. They take the shape of the container completely, but if you spill water, it sort of runs around. And so water is not as fixed in shape as solid, but more fixed in shape than gas, right? Because you can still see an edge of water when you spill it on the ground, whereas gas is sort of just filling up whatever space it can. All right. So what do you think would happen then if we talked about how things move around based on energy, and energy was related to temperature? So what would you think if there's a bigger thing versus a smaller thing, right? So here's a giant rock and here's a little rock. How much energy do you think it takes to make things move around? And hopefully you realize that things that are heavier are harder to move around. So heavier things tend to be solids because they don't move around as much, and things that are lighter tend to be gases. And we'll talk about that I guess I can talk about it right now. Periodic table, which is all the way back here. All right. So these are masses. No, maybe it's there. I can't read it. Oh, there it is. There's a number. So the masses get heavier as you go down. If you look at these numbers here, they get bigger as you go down. So things up here tend to be um, gassy, and things down here tend to be solidy because of that fact, because it's harder to move. And there's other factors that involved, and we'll get into that. Hopefully that doesn't make you dizzy. But hopefully it makes sense that if temperature is movement, it's harder to move something bigger than smaller. So you need to have a higher temperature to move the heavy things, and a lower temperature can move lighter things just as much. All right. We typically measure temperature in Celsius, but we use Kelvin in this class as well, because Kelvin, as you learned from the FET, is based on motion. And the motion is that if things are moving, there's some measure of that movement. And if you slow it down to where there's no movement, we would say that's 0 Kelvin, and therefore nothing is moving. And so this would be 0 Kelvin. That would be very cold. And anything that has any motion would then be considered warmer than 0 Kelvin. So that's why we use that. If you're converting this, which is a pretty easy math thing for us to do, you basically have to add 273 to the Celsius. So whatever the measured temperature is in Celsius, you add 273 degrees, and that gives you the Kelvin scale. So if we had 100 degrees Celsius and we wanted that in Kelvin, we would simply just add 273 to 100, and you would have 373. So that would be 373 Kelvin. If we had negative 23 Celsius, that would be negative 23 plus 273, which gives you 250 Kelvin. Okay, and you should be able to go backwards as well. So if I tell you something is like 303 Kelvin, then you would have to subtract 273 to figure out what that is in Celsius, and that would be 030 degrees Celsius. All right, so you should be able to go backwards and forwards with that. All right, and you should know these changes of state, which again you should have learned before now. But if you turn something from a solid to a liquid, that is melting. If you turn a liquid to a solid, that is freezing. If you turn something from liquid to gas at any temperature, it's evaporation. But if you do it at I don't love this distinction, but if you do it at a higher temperature, then we call that boiling. Gas to liquid, you can talk to me about that during class. Let's see how that goes. But anyway, gas to liquid is always going to be condensation. Solid to gas, these are the ones that you don't really think of, but it deals with dry ice. Solid dry ice goes right to a gas, goes right to carbon dioxide, and that is called sublimation. And if you go backwards and turn that gas right back to a solid, that is called deposition. I think that's everything you need to know. There you go, kids. Everything you need to know. So hopefully that was helpful, and study up for your tests.